I guess I'll say apologies in advance that you get to listen to me again and not Shushu. She wasn't able to make it here, but I've definitely appreciated working with her. She's been able to do a lot of the modeling work, being able to investigate another method to be able to look at mitigating spike fatigue failures, but in this time it's using glass fiber reinforced composite cross ties. And even though we're talking about glass fiber reinforced composite cross ties, I would say some of the conclusions at the end hopefully will be able to relate to other composite people who are interested in other composite tie types. With that, I do also want to thank all of our industry partners, FRA for funding, and also EverTrack for providing the GFRC ties. Another map of where we're going to be going. I'm not going to spend much time on the background and motivation. Christian did a nice job being able to highlight that. I'm going to spend more time focusing on what were our laboratory results. What did we see in the literature? How do composite ties actually compare to timber ties? Be able to give us some numbers and visuals to be able to help us understand how these compare, and then be able to go into the details of a finite element analysis that Shushu has done with us, and then the final conclusions. Christian hit on this. Definitely a widespread problem. And I know there's work looking to be able to figure out how can we find these with a non-destructive evaluation. And if anybody has any ideas, you should go talk to Cam, because he's always looking for good ideas to be able to go out and find these without walking the track and tapping every single spike. And as Christian mentioned, there's multiple mitigation approaches, and what he was hitting on with these screw spikes and spring washers, that's a fastening system approach to be able to solve the problem or be able to help mitigate this problem. We have some operations related options that might be able to work that we want to go out and quantify in the field to be able to confirm that these actually could help as well. But what I want to talk about through this talk is a tie-related solution. That way people have other options. You can come at it from a fastening system perspective, operations, or a tie perspective. And this work was carried out in the lab and the models. And some of the motivation for this came because whenever we were doing our initial modeling, we find that timber ties in this perpendicular to grain direction. When I say perpendicular to grain, I'm referring to the direction that's going to be taking these longitudinal loads. It crushes due to these low strength values. And we'll see later on that they're about an order of magnitude weaker in this direction than they are in the long direction, which would be subjected to the lateral loads. And whenever we look at the differences in strength of compression strengths of this perpendicular to grain timber versus this compressive strength of the glass reinforced composite tie, there is a big difference in strength. And this big difference in strength should be able to give us a benefit because we'll no longer be crushing the material. That's our goal. And so if we don't crush that material, the spike can't bend as much. And without that additional bending, then we won't fatigue fail it. That's the goal. We're looking at GFRC, single spike blocks in timber, as well as our finite element modeling. The order of the rest of the presentation will be first looking at the spike load characterization in the laboratory, and then being able to look at the effect of composite engineered properties. And I'll start with some of the lab work because we wanted to prove this out before really diving into this, doing an extensive amount of modeling. We wanted to figure out, is there actually any benefit to it all? And so we took an instrumented spike, drove it into a composite tie and timber ties, and started comparing the strains to one another while applying a longitudinal load to that spike. And I'm just going to throw up the strains. The strains are each of these individual dots that came from our instrumented spikes. We're looking down into the depth of the spike and comparing it to timber, which is in this orange, and all of the composites that we tested, the GFRC ties, replicates that we had are in the other colors. And we can see that at our inch or inch and a half, we have a 20% reduction in strain. So immediately we see that there is a benefit. There is a reduction in strain in the spike when we're installing it into a composite tie with a high strength. because we're not getting that crushing. We then wanted to take this step further. We wanted to look at cyclic loading, because one load is great, but what happens whenever we actually start cycling this, because it will undergo cyclic loads. We were able to successfully do this in timber, but once we threw it in a composite tie, we started breaking things a lot. But we came up with a redesign so that we could actually run the tests. This is just a video showing what this test looks like. And one of the reasons why I show you broken components is you'll see one of our tests has a slightly lower number. But this is just generally what it looks like. And whenever we look at our results from our timber cross ties, the first rounds of shakedown with the timber tie, we were trying to figure out what load magnitude is going to create failure in a reasonable number of cycles. And so we landed on going right up to about 2,300 pounds, cycling from 200 to 2,300, and we got failure. We ran this again and got failure in less than 1 million cycles. And so 1, we were able to reproduce the failure, and 2, we were able to do it in a reasonable number of cycles. Whenever we threw these spikes in the GFRC composite ties, we were then able to see that we were not able to reproduce the failures. We broke our fixture, and then we were able to load it for more than 5 million cycles on another couple trials, different spikes and different ties, and we're not able to reproduce failure. And so we wanted to start understanding, why is this occurring? What are the benefits of a composite tie over a timber tie? Can we actually give more guidance to say you should be targeting a specific modulus of elasticity, a specific compressive strength? What should we be aiming for? And that's what led us to our detailed finite element analysis. And the first thing we wanted to do is create it and validate it. And again, Shushu did a wonderful job working with us. We again used one of our instrumented spikes, and she was able to look at the test would be our laboratory value coming from our instrumented spikes, and the model is what she is outputting with her developed model. And at both 1 inch and 2¼ inches into the tie, she gets very good agreement with her model. And so we considered this to be a validated model, something that we could use going forward to do a sensitivity analysis or a parametric study of changing the materials. So where do composite ties fit relative to timber? If we look at modulus elasticity, the first thing we notice when we compare parallel to grain to perpendicular to grain, that again, I alluded to this, there's an order of magnitude difference. It's about 1/10 the level. So that means it's a lot more squishy. And composites, yeah, they're stronger than timber, or they're more stiff than timber, but not much. Even the GFRC, which happens to be an outlier, is still significantly lower than the timber parallel to grain. So whenever we look at this values, one of the reasons we wanted to do this, not only to compare it, was to come up with what are reasonable values that we should be putting into our model. It'd be one thing if we said modulus of elasticity makes a difference if we go to 2 million, but if you can't make a composite tie that's 2 million PSI, then there's no reason to do that. So composite ties, slightly better than timber, but much lower than timber parallel. But if we go to compressive strength instead of modulus of elasticity, compressive strength, again, about an order of magnitude lower perpendicular. That's why we crush the timber all the time. But now these composite ties, even the median value is about 5 times higher than timber perpendicular. So this is something we can start working with. We might not be crushing any sort of composite material that's out there. And this GFRC is substantially higher even than the timber parallel to grain. So now this is something that could provide a very good benefit to reducing the amount of crushing. And so this again gives us a range of values that we can play around with in the model. Shushu then wanted to understand, what is the effect of this elastic modulus? Is there a benefit to changing a modulus? Should you target something softer or something more stiff? And we put in a compressive strength that would not crush. We made sure that it was very high and would not crush. And then we changed the modulus of elasticity values from the bottom end all the way up. And we can see that there's about a 5% reduction. So it's not that large of a difference. You're not gaining a lot by going to a higher modulus of elasticity when it's talking about reducing the bending strain of spikes. But what about compressive strengths? Again, we're applying a 2,000-pound longitudinal load. And whenever we look at our values, originally we're above our fatigue limit. So we would expect failure to occur whenever we have only 3,000 pounds or 3,000 PSI material, composite tie strength, compressive strength. But as we get stronger, we end up going below that fatigue limit at this specific 2,000-pound load. But one thing to notice is once you get above, it actually happens to be about 4,300 PSI in this case. Once you get above that, there's no benefit. It doesn't matter if it's 5,000 PSI or 6,000 PSI, you're not gaining any benefit. So there's no reason to actually go up to that high of strength if this is the problem you're trying to solve, which is good information to know. And so how does this again compare to timber? We're trying to hone in on a specific compressive strength, a specific modulus of elasticity, but if you can come up with your perfect idealized composite tie, how does it still compare to timber? And we'll have GFRC in blue compared to timber, perpendicular in red, and parallel in orange. And at a high level, we see that there is certainly a benefit to the composite tie over timber perpendicular to grain, but it's still not quite as good as that parallel to grain. And it's because of that lower modulus. And so this is to show that a composite tie can help. It can reduce the amount of strain in the spike. At 1,000 pounds applied, you're going to reduce the strain by 13%. At 2,000 pounds, it's 26%. So these are definitely values that are noticeable. But being able to come up with a specific compressive strength to target depends on the amount of load that you're going to be applying. This is all basically applying 2,000, or in this case, 2,500 pounds. So we need to optimize for a given loading environment, or you could optimize for a given loading environment. That way you can say, I have these composite ties that don't meet this compressive strength, but I'm still having broken spikes. If you know generally what the longitudinal loads are, perhaps you're a transit agency that has seen these failures, then this could be something to look at, because for a given modulus and a given load that's being applied to your track, what is the required compressive strength that's going to be needed to be able to achieve it? And so Shushu has been able to develop this model that can give you an output and be able to help identify what type of tie you need for a given loading environment. And an example way to look at this is at 1,700 pounds, which this is a 95th percentile longitudinal load at horseshoe curve. You would need 1,000 PSI modulus at about 500,000 PSI. 1,000 PSI compressive strength if the modulus is 500,000 PSI, or 2,200 PSI if you have a lower modulus. So it definitely makes a difference of what your strength is depending on your modulus given a certain loading that's going into your track. So high-level conclusions is that the laboratory experimentation demonstrates that longitudinally loaded spikes in GFRC engineered composite cross ties do experience lower strains. They didn't fail in cyclic tests, and our validated model showed that compressive strengths have a greater impact on reducing the strain than modulus. And ultimately, if we ask the question, can composite ties potentially be used to mitigate broken spikes? The answer is yes, potentially, but definitely more work would be needed out in the field to see, is this going to work? And is it economically feasible to be able to do so? So with that, thank you again to FRA and all of our sponsors for being able to help us achieve this work. And if you have any questions, certainly ask me, or reach out to Shushu. She's sorry that she can't be here.
Any questions for Marcus?
0 for 2.
Well, thank you.